So, as you can imagine, we're going to spend most of our time in the realm of the reference ellipsoid. And this is also, when we're talking about an oblate ellipsoid, when we're using the term reference, it's the referencing the shape, the model of the shape of the Earth that we're doing. So when we use that terminology, just kind of keep that in mind. So we could talk about a reference ellipsoid, a reference sphere, as those are the primary two models that we use. Okay? So the first thing that we do is we transform the shape from the geoid to the reference ellipsoid. So we're generalizing it, right? And then we have to adjust the datum as well. And we'll talk both about the horizontal and vertical datums. But just think more of the surface. We're approximating the shape, but also the surface of the model. And literally what we're talking about is an oblate ellipsoid. So think in terms, an ellipsoid is three-dimensional. I always like to call it the egg, right? Doesn't it look like an egg? Use your worst imagination. So that it's just slightly off of a sphere. It's a little bit wider in the center and shorter and flatter at the tops and the bottom. And we can actually measure how much it is off of a sphere. We can use that number. So if it's a perfect sphere, we would have a 1-to-1, right? That the axis, the two different points would be equal to 1. But when it's slightly off, one line's a little bit longer than the other. So that model and that amount that it's off is the measurement that's used to reference the different reference ellipsoids. So GRS 80, WGS 84, Clark 1866 have slightly different numeric values. Okay? And I think I got a better example here. So WGS 84, which is the most commonly used ellipsoid worldwide for GIS purposes, is 1 to 298th off of the sphere. And I'd like you to know this graph. Like if I say, can you graphically describe to me what the definition of a reference ellipsoid is? It's a certain percentage off a sphere. It's literally the formula of B over A. So B is always going to be a little bit shorter. A is always going to be a little bit longer, right? So 1 minus B over A. And that's where we're getting that 1 to 298th. Pretty simple, right? If B and A were the exact same numbers, it'd be a sphere. So that's actually the next generalization that we'll do in our model of the Earth. So A is a slight bit, is 378 to 356, slight bit bigger, and it doesn't quite equal 1. So there's different models of this shape, different reference ellipsoids, but we need to also use a datum with the reference ellipsoid. So we need to know our shape and our surface. So when we're thinking of, well, if a geoid's really precise when we're using it to track satellite motion for the GPS satellites, or targeting smart bombs and those kinds of things, or doing extremely precise surveying for, let's say, erosional purposes in the Grand Canyon, that kind of stuff, the ellipsoid is really good for large-scale maps, like the topographic maps, like the work that's done within state planes coordinate systems, like the work that could be done in a major metropolitan city, all right? That kind of a scale. It doesn't quite reach to the level of a state, maybe a really small state or a really small country. Luxembourg, Rhode Island would work fine, but you're not going to get huge coverage. But that's where a lot of the GIS work goes on. So we've been talking about the ellipsoid. Let's switch and talk about the datum, because we need to use both and put them together. So the definition of a datum is literally a set of numerical values that serve as a base for locating geographic features. Right? It's just a baseline, if you will. But it does so both in terms of horizontal base, like X and Y, where are we standing in a grid, but also vertical base. Mean sea level is actually a vertical datum. All right? How do we know how high up we are or how low we are? How do we know where we're at horizontally? Did you want that? So when we deal with datums, you can kind of think, and comes from the, it should still be up, might not be the same website. If you do a search for NOAA and like Introduction to Geodesy, there's some good little tutorials on there. That's where I stole a lot of these graphs. If you think of the National Spatial Reference System, and then they're kind of comparing it to like building a building, right? That we have our horizontal datums, we have our vertical datums. They provide the foundation for our geographic information infrastructure. And then we think of the structures that we build on top of that. We put the buildings, the walls, the framework, the roof. Over here, it's the different layers of data, land use, population, topography, that fit on it. And then you do schematic blueprints of the building. Over here, you do your topographic maps. You do your thematic maps off of that. Okay, so that's kind of where we're getting at. That this is really providing the foundation for doing your mapping, for your accuracy. So this is my buddy Avram. Took this picture. Where is Avram, roughly? We're talking about vertical datums. Yeah, that's Mount Everest back there. If you have gone to the top of Mount Everest and want to replace Avram in my slide, please send me an updated picture. Why Mount Everest? What is Mount Everest? What do we think of when we think of Mount Everest? Highest point on the surface of the earth, right? Or highest mountain on the surface of the earth. Oh, but what about Hawaii? The Big Island. Actually, if we put Hawaii, the Big Island, and put it at the same datum, the same baseline as Mount Everest, which one's taller? Hawaii's taller, yeah. But it's just sitting down below sea level. Oh, so you're starting to see the problem with vertical datums? So then let me ask you, what is the highest point on the surface of the earth measured from the center of the earth outward? Is it this one, or is it somewhere else? You don't know these things? How about Mount Chimborazo in Ecuador? That was just on the tip of your tongue, wasn't it? Yes, in Ecuador. Actually, yeah, because we know that the equator moves further out in terms of from the center of the earth than any other point. And then we compare it. Can I read it here? It's Mount Everest. Ugh, so bad. 3,900. Anyway, trust me, it's further out than Mount Everest. You can look it up, and if I'm wrong, let me know. If I'm wrong, let the National Geographic Society know. They are the one that I stole that graph from. So yeah, if we can think of doesn't it make a difference where your vertical baseline is that you're measuring off of and how you're measuring? And that was kind of the idea, that I wanted to just choose 3 different points in how we measure things vertically. What is height? Well, height's relative to what we're measuring height off of, right? And how we actually do those measurements. And I will even confuse you with how we even do measurement is relative to how we've created our measurement systems. You know, that they're really cultural constructs that are agreed upon by convention and not by some preordained fact that occurred before us. And you'll say, well, wait a minute, what about the meter, right? Isn't that based on the Earth's surface? So, no, no, no. The meter's a lie. It's actually incorrect. And they keep having to update the convention to correct for human error when they did the original measurements. So the meter doesn't refer to the Earth's surface now, right? Do you know what it refers to? It's the distance, the amount of light travels for a certain period of time, right? Because the original block of meter that sits in Paris, France, keeps degrading, and, keeps eroding a little bit, falling apart. So, all right, this is a regional one. Where are we now? Yes. El Centro, yes. If you do the car ride from here to Esri in the summer regularly, and you go down Interstate 8, you head out past El Centro, and you're going, I just can't wait to get over that hill and feel the moist breeze of the Pacific. Yeah, you're actually under sea level in southeastern corner of California. So the first in the United States vertical datum that was accepted was the National Geodetic Vertical Datum from 1929. They used different points of elevation to define what was sea level. So you see where I'm going? This is what's known as the sea level datum. So if you're in El Centro, bring your wetsuit. Literally, and I took a quote out from the National Archives of what the datum referenced. Mean sea level was held fixed at sites of 26 tide gauges, 21 in the U.S. and 5 in Canada. And so they kind of looked at tides over a period of time and said, we establish that as 0. Can you, just as being critical thinkers and graduate students, think of problems with this logic, of how this might not remain constant, or issues that could occur that would change the value of sea level since 1929? Oh yes, that little thing. That might cause some issues, right? Couldn't tides vary annually, the pull of the tides and how high sea level could be, and all kinds of unknown factors. In the on the Atlantic, they had they've had similar climate change variables of ice melts that impact the New England area and makes the tides higher and lower at different times. So you can think of how that could be problematic, so to speak. So in 1988, they updated the vertical datum, and you can kind of imagine that's right around when they did the horizontal datum, which we'll do in a minute, the NAD 83. And then they established it in 1991. And this is where they used satellite instruments and kind of tried to iron out the differences. And the map you're looking at is a contour map depicting height difference between NAD 88 and NAD and the 29. And yes, this is millimeters, mind you. So it's not, it's dramatic in some places, like the Rocky Mountains. You see this one here? Little agricultural geography. You know what that is? Yeah, it's the San Joaquin Valley in California. What's in the San Joaquin Valley? Oh, other than that. It's like this is the breadbasket of the United States. This is where most of the rice is grown. I mean, this is where a lot of our agriculture comes from. And subsidence. Huge amount of groundwater pulling out creates subsidence. And so we see different values there as well, too. So I always am amazed when I see that. But you can see how mountains cause problem with vertical difference. And there's actually negative. Where are we now? Okay, I'm biased towards the United States. I apologize, but yeah. How do you know Denver? Or what is Denver known as? The Mile High City. Well, there's kind of an issue, though, of that people want to take their picture on the steps of the, I think the City Hall, Denver, or the Capitol. I'm not a Denver political geographer, so bear with me. What step do I stand on? Well, so you have 3 different vertical datums. You have the 29, 91, and then there was one in between. Do I actually say what they are? Oh, yeah, so here we go. So after all these years, we finally got it right, Colorado Governor Bill Owens declared, shortly after setting a 3.5-inch standard bronze disc, that one, on the 13th step. So everybody that took their picture before 2003 didn't count. So the first mile-high marker was actually installed before NAD 29, or NAVD 29, on the 15th step, and was done because of the Transcontinental Railroad. If you think of that, you know, the railroad came pretty close to around there, and they had to measure that to figure out how they're going to get the railroad from somewhere in the middle of the country over to San Francisco. The second marker, brass cap, set in 1969 by Colorado State University engineers, was used to demarcate NAD 29. Oh, look at that. The dimple for the exact elevation. That's just university nerds there at that point, right? So, but I'm giving you just some fun geographic points of it, but you can see how what we measure from, how much variation that we could possibly have with this too. So just to give you an idea of elevation change and then get a little bit more close to home, or at least home as we talk about right now in Tucson, look at how much difference we can have in Arizona. That the Mogollon Rim and the northern part where there's more elevation, and you can even see Mount Lemmon, Catalina Mountains, how it's increasing. You get between 1 foot to 4.5 feet of variance in elevation height, depending on which one you're using.